everybody who's going to come is here already, so we'll get started. I've already started saying the and I watched myself at the last speech I did, and I cringed so much at the amount of times I said So if I get into this habit, can people start doing this to me or something like that? You know, aversion therapy, and maybe I'll start getting out of this habit of going We're going to be talking about Oracle Application Server today and format string exploitation on the Windows platform. We're not going to be looking too much at the Oracle stuff, but we will be concentrating more in the area of format string exploitation on the Windows platform. If you're after the Oracle, you know, more information on Oracle, then Eric Burkholtz's book on special ops, he's just published with Shingress. I do a chapter in there, chapter 13, on Oracle security. Am I saying Sorry. You did it. And keep on, please. So, yeah, that's going to be one of the best-selling books, I think, for Shingress. It's got a lot of good information in there. So, if you get a chance to have a look at it and maybe buy a copy for Eric, then please go ahead and do so. So, who am I? I'm David Litchfield from NGS Software. I'm doing again. We write software, do consultancy in the security area, basically. So the introduction, we're going to be discussing format string vulnerabilities. Most of you in this room will already know about format string vulnerabilities and probably know how to exploit them with, without batting an eyelid. They've been known about for a few years. Tim Newsham documented them pretty much in the first instance whilst working with Gardant. Very good paper. They're well documented on the Unix platform, but less so on Windows. So that's why I'm going to be looking at format string vulnerabilities today. You always find yourself, when you do these talks regularly, looking for something interesting that you haven't done before and hasn't been done to death. And I don't think format string vulnerabilities have been done, so that's why I'm doing that. I was initially going to be speaking about the Microsoft locator buffer overflow, but then again, it's just a simple buffer overflow, no real value in then talking about, here's another buffer overflow, here's how you exploit it. So I was waiting on Oracle patching these vulnerabilities before I could confirm that I could do a talk on this. So this is why there was been a change halfway through. So what are format string vulnerabilities? Some of you in this room will probably know what they are, will not know what they are. Essentially, within C, you have a family of printf functions, and they essentially take a string and, well, certainly the printf function on its own, and prints it to the console. So we have a simple C program here, printf, hello world. Anyone who studied even a modicum of C will recognize this program from Carnegie and Ritchie's C, programming. This is where the hello world program comes from. So printf essentially takes a character string and prints it to the screen. There are a number of other printf functions in the family. There's fprintf that takes information or data and prints it to a file. sprintf that prints the data to a buffer or copies the data to a buffer. vprintf for when there's loads of arguments and so on. syslog is vulnerable to format string vulnerabilities on Unix platforms, but there is no, or I don't believe there's an equivalent on Windows. The C++ string object, format V, uses vsprintf underneath the underlying mechanism, so that's another one to watch out for. Now, it doesn't just, with the printf functions, there are things known as format specifiers. So when you're dealing with dynamic data, you can basically have a format specifier, this %d here, that takes an integer value and replaces whatever that integer value is and pops it in there, basically. So we can begin to control with dynamic data what goes into the printf statement. So this part here is called the format string. Now it can take a variable number of arguments, so we could be like the value is %d, 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 and just have 3 devals basically, so they're all being pushed onto the stack. There are other format specifiers such as %x. %x takes a hex number, an integer and puts it in hexadecimal format. There are several format specifiers. %c takes a character, a single character. %d is a decimal. %e is float or doubles in E notation. %f, a float or a double. O, octal. P for a pointer, S for a string. X for hexadecimal, and I for an integer. We also have width specifiers. We can basically say if we want a hexadecimal number, let's say dval has the value 3, but we wanted the value 0.000003 printed out, we can specify its width with the .8x. That would print out 8 characters basically. We can also use high and low. %hx says show us the high order bits, %l the low order bits, and so on. You'll see these will come in useful later on. One specifier I did not mention is the %n specifier. Now this is really where the root of the problem lies. We'll get to why in a minute, but essentially the %n specifier essentially allows you to write the number of bytes which have been output to a variable, and you pass that variable in a pointer to it there. So essentially, if we were to compile and run this program, we are printing the characters 1, 2, 3, and 4 to the console. We're then using the %n specifier to write to this variable here, int x. We pass it in as a pointer, and that would say the number of bytes formatted is %d. Now, 1, 2, 3, 4 is 4 characters have been printed to the screen, so 4 would be written into the x variable, and then we return the program. So the %n specifier allows us to write the number of bytes which have been formatted up to that %n specifier to a variable, and a pointer to the variable is passed on the stack when you call the printf function. Okay, the problem arises when no format string is passed in, just the character string, the variable itself. When there's no format string passed in, if a user or an attacker control the input, they can basically specify their own format string and embed the %n specifier and begin to overwrite arbitrary locations in memory. This can be done to execute arbitrary code. It can be done, to cause logic corruptions. For example, if there was a structure that, specified someone's credentials and 0 was, the equivalent of system or root, then we could if we could locate that structure in memory, we could overwrite that with, nulls and become equivalent to root or system or whatever the, access control mechanism is. So here we have a sort of vulnerable program. What we're doing is taking arguments in, and whilst we have a list of arguments, we're just printing them without a format string. So we take the argument and just print it, and then loop round whilst there are arguments. So if I show you this, C:\fmt. If I just send hello, can the people at the back see that? Or is it, let me see if I can change the font size. I'm sorry? Yeah, sure. Okay, this is me running the program here. FMT is the name of the program, and I pass in an argument hello, and it just prints hello back to the screen. We get strange things happening though when I go hello %x, 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 %x. You can see here, we still have our initial hello, but then we've got a list of numbers that are coming from somewhere. Now this is because we're providing, as the user, the format string, and because that's the first argument going on the stack. If we look back at the source code, the first argument being pushed onto the stack is the pointer to the string being printed. Now the printf function, or family of functions, expect the first parameter being passed to it to be the actual format string. So what happens is by us passing our own format string as the first parameter, it takes that as, this is the format string we should be using, and starts taking things off the stack and using that. So this is what's happening when I run the program here. We can see, actually, if I do it this way, %x, 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 so we can tell what's on the stack essentially. We have a 1, something that looks like a stack address, 12ffco. That's probably a save return address, 40112D. Then there's a 2, then 300ECO, which probably looks like it's a something to do with the heap. So we're essentially taking things which are layered on the stack, basically, and moving down the stack space. In terms of attacking, we know using the %end, let me show you that as well. What I'm going to do here is using the %end specifier is, just put several of them in there to ensure a crash. Okay, we get a crash in the program, an access violation saying the instruction at 401742 reference memory at 000001, the memory could not be written. Now, remember going back to here, the first thing on the stack was 1. So we can look at that and go, well, wait a minute, that's interesting. We have that 1 is come up here, and we're trying to write to that address. Now, I presume that if we go, the next thing looks like it's writable because it looks like a stack address. So if we go %x, %n, we'll probably get away with being able to write to that location. And indeed we do. There's no access violation. As it happens, that's probably the saved base pointer that we're overwriting there. So essentially, you can see that using the %end specifier, we can begin to overwrite or attempt to write to areas of memory. Now we can control that. Well, I'll show you how to do that later on. But assume we want to run arbitrary code as opposed to just exploiting, overwriting a structure with zeros or an arbitrary number that gives us higher levels of permissions. If we want to run arbitrary code, we can choose to overwrite a save return address, which is stored on the stack. For those of you that know buffer overflows or how to exploit buffer overflows, you would overwrite the save return address to gain control of the process's path of execution. Alternatively, we could overwrite a function pointer. We could overwrite an exception handler, or the unfiltered exception handler as well. So now, the way you approach exploitation of a format string depends upon whether your format string that you supply exists on the stack or the heap. If it's on the stack, we can control what's on the stack in terms of the string. So we can put arbitrary memory addresses in there. If your format string that you're passing in is stored on the heap, then you're basically stuck with what's already on the stack. So, I mean, whilst working with that stake, Ollie Whitehouse found a format string vulnerability in Van Dyke's vShell server, and I had the benefit of being given the opportunity to write the exploit for that, which was quite interesting because that was the first time I'd ever really tackled this as a problem. And the way I did that, because it was using basically the format V from C++, which, as I said, was passed down to VSPrintf. Now, because it was a C++ object, it was all stored on the heap in terms of the data. So we were stuck with basically what was on the heap, and I overwrite, in the exploit there, which is published on the @stake site, I overwrote a function pointer that basically pointed back into, which I pointed back into where my arbitrary code could be found. So if you go to the @stake website and wanted to have a look at that, you can play with that. The other interesting thing with that vshell one was essentially you could not use any characters other than A to Z, 1 to 9. So it was, I had to write, the arbitrary code using only those characters, which again was the first time for me. So you have this bridge building technique where you're writing the code as you go on, and the two finally meet, and execution continues downwards from there. So the object is to overwrite something that controls the program's flow of execution. Now I'm just going to give you a wee example. What we have here is a vulnerable program called vuln.c that takes in character input, takes in an argument from the command line, copies it to a buffer, and then prints that buffer to the screen. This here is where the vulnerability lies, where we can see the here. Basically, we'll be passing in our own format string to gain control, but we'll do it in stages. So, I'll walk you through the steps. Okay. First off, I'm supplying 4 A's and a %n. No problems there. This is because the next thing on the stack is writable. So we then start extending it out. Oh, that's why I'm doing this, I see, right. What I'm going to do is get this to crash. Okay, where the problem lies is basically here. You're not going to see that, so I'll have to read it to you. Basically, we have I can't see it either, so we have a move ECX into dword pointer EAX. Now, that's the assembly behind this. Now, essentially what that is saying is, take whatever is in ECX and move that into the address pointed to by EAX. Now, we have to question then, what is ECX? Can we control that, and can we control EAX? Well, EAX is currently 41, 41, 41, 41. We can control that because that's our first 4 A's here. ECX essentially is the ECX register is here. The number in there is 4. Now, essentially, we have written out using the print, formatted 4 characters. If we then, and 4 happens to be in the ECX. If we then do, 8, if we format 8 characters, we can now see ECX has 8. So, as you'll have probably guessed, the number of bytes that have been formatted go into ECX. So if we're wanting to overwrite a save return address or a function pointer or anything like that, what we need to do is get into ECX, the address of our string. So we need to form, let's say our buffer where we're going to put our arbitrary code can be found at address 0012ff00. What we need to do is write that many bytes out with the printf statement. And so that goes into ECX, and then overwrite a location of our choosing. So let's stop debugging that. Now, in terms of getting the right number, we can basically use the width specifier here. This essentially is %.622496x, %.62249x, %n. So you can see all these zeros scrolling off the screen here. That's because we're, formatting, 62,000, 620,000? Yeah, 620,000. Now we have an access violation. If we debug this, we can see in ECX now, we have 0012ff40. If we go to that address, it's not the location of our code, but it's there or thereabouts. So we'll be working with this and manipulating it as we go on. But essentially, we're in the right kind of area to find our buffer. So we've so far, got the right number or thereabouts the right number of bytes formatted. This time we're going to put some space in the thing we're requesting. This is where our buffer, our shellcode will go essentially. So we've got about 40 A's there, and that same %.622496x format with specifier. So I'm just letting that run because it's quicker. There's our access violation. And this time we see we are attempting to write to address 414141, which is obviously taken from our uppercase A's. So if we debug that, and then start rifling through the stack to see whereabouts our format string might be. There we go. So there's our buffer here. We have our A's and our format specifiers here, basically. So that is at address 0012 FD84, there or thereabouts. We still have an ECX 0012FF40, and that's because I dropped the number of, in terms of the width specifier, to compensate for the number of A's, basically. So we know we can write to an arbitrary location, and so on. Let me just get rid of this. Okay, this time we're doing the same thing. We've got a few more %x specifiers here, and then BBB on the end, 4 Bs. Now, the reason we put more %x specifiers is because we're currently trying to write to somewhere here, and this is on the stack. So what we want to do is skip over these A's here, like this, over these X's, and then into, these BBBs is what we're looking to write to, which would be 4242. So we request this, and it's not going to work. We can see we've overwritten here. Well, we're attempting to write, rather, to address 7825, 7825. Now, that is %x, %x, %x. So essentially, we've come down into, we're writing, we're pulling address out of here and attempting to write, out of there. So we still have to put some more %x's in to try and get us to these BBBs. So this time, we've put in a few more %x's essentially. This time we should attempt to write to 424242. Okay, so the instruction at 401868 reference memory at 42424242. So we've now found our B's in terms of where it's located on the stack. So we've jumped over using these %x's here. We've jumped over. For each %x, it's 4 bytes basically, and we're jumping over, and now we're trying to write to there. So instead of using BBB, what we'll probably do is, find out where our buffer can be found on the stack, find a save return address on the stack, and overwrite that with the address of where our buffer can be found on the stack. So if I open Notepad 1.c, because we can't easily write into a command prompt 0012FF00 kind of thing, we essentially need to call another program that will execute this for us. So we're going to be setting up our format string using another program, and then essentially just calling system and passing buffer in, which has our format string, and calling the vulnerable program. At the end here, let me increase the font size so you can see this font. At the back here, you can see where our BBBs were. We're now attempting to write to address 0012FD54. So if we run the program, okay, we get the instruction at 0012FF83 reference memory at an arbitrary location. Now that's interesting. We've managed to overwrite the save return address with a pointer to our, with a pointer to somewhere on the stack, because that thing there is a stack address. We should be, if it was in the program itself, it would be the address at 0040 blah 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 at reference memory. But we're now back on the stack and executing code on the stack. It just so happens that there is no code on the stack. That's why we have this access violation. So we then notepad 2.c. This time we're going to put some breakpoints. Again, if I increase the font size. So essentially it's the same string, but immediately after that, we're going to be putting some breakpoints on. CC, hex CC, is the hex representation of a int3, which is a breakpoint. In other words, stop execution at this point. And if we run this program, we should get a message pop up on the screen saying breakpoint reached at address on some stack address. So, okay. The exception breakpoint, a breakpoint has been reached, occurred in the application at location 0012FD80. So we've landed back in the stack, we've overwritten the save return address with a pointer to our code, and now we're starting to execute code on the stack. It just so happens our code we're executing is an int3, which is breakpoint. So it's nice to see that we're now back on the stack. So if we want to then run an arbitrary program, notepad 3.c. What this one does is basically we have our exploit code, 55.8b EC. People should recognize that as the procedure prologue. We're essentially, this is where our exploit code is starting. We're simply calling system, winexec, and executing, a shell. So if we run this, essentially, remember we're having to write to ECX a large number of bytes to, that is equal to 0012 FF, whatever it was. So that's why if I alt and tab away, it will go much quicker. Okay, so the exception breakpoint has been reached. Now, if I move that, you can see we have here, again, let me increase the font size, properties, font. Okay. We have here Microsoft Windows 2000, version 5, blah, 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 copyrights and everything like that. So we've got our shell, essentially. Now, the reason we've got a breakpoint there is because I don't terminate the program properly. It's for demonstration purposes. This FFDO is our call EAX. We essentially put into EAX the address of WinExec, call EAX here, FFDO, and then set a breakpoint. That's CC on the end. That's why we get that breakpoint coming up. So that essentially is, running through, taking a vulnerable program and trying to explain it. Now, before getting on to our Oracle application server and its format string vulnerability, are there any questions about that? Did I make myself clear, or are there any points I didn't make clear? Is everyone cool? Okay. Oracle application server. Great product, highly, highly functional, caters for pretty much every developer's taste. If you want to code in PL SQL, you've got it. If you want to code in JSP, you've got it. Java, Perl, Fast CGI, it's there and ready. Oracle Application Server is based upon Apache. And with the latest incarnation of Oracle Application Server, we have something called ORADAV. Now, ORADAV is essentially WebDAV, WebDAV being the web distributed authoring and versioning system, essentially turning the World Wide Web into a glorified file system. It's a modification. In terms of Oracle's ORADAV, it's simply a modification of the moddav, which is like the real Apache version. Now, they've modified it in a couple of ways. One of those is to log bad gateway errors, which moddav by default does not do. But if we look at the source code for moddav in davutil.c, there is a function, dav lookup URI, which when called, essentially says the destination URI refers to different scheme or port. Now, what that's essentially saying is here we have %s, which is the scheme. So that's like HTTP : or HTTPS, and they want something else. Now, there's also another area where the port number is different. So if you telnet enter port 80, but you say the scheme with the copy instruction is port 999, then essentially you'll get another bad gateway error. The thing is with moddav, this code is never executed because they don't log bad gateway error messages by default. Oracle have modified the code so they do actually log these. So this is a problem waiting to happen if moddav were to suddenly start logging bad gateway errors. So they really need to change. Now, essentially, what happens is we call dav lookup URI here. We're taking in user input here. I'll demonstrate this in a second. So the dav lookup URI function is called. We're taking user input here and assign it to result.error.description. Now, once that's been called, we then say if it's a bad request, log this error, ap_log_r error, and we take in that user input, lookup.error.description. So we can control what's going on. Now, this is the format string vulnerability. It doesn't look like one, but it actually is. It's simply because the Apache log error, basically, is the underlying code beneath that calls the printf family of functions. So in terms of exploiting this, let's talk about WebDAV for a second. Essentially, WebDAV is turned on by default with Oracle Application Server, which is a big vulnerability in and of itself. We can upload arbitrary scripts and so on and gain control by using a couple of other flaws that allows us to traverse the tree using JSP and so on to execute arbitrary JSP code. By default, if you uploaded the JSP and without these other bugs, you can't execute the JSP within there, but there are other ways to gain access to it. But more interestingly is this format string vulnerabilities, because they don't occur frequently on Windows platforms, and when they do, it's good to discuss them. So if we quickly go over DAV, essentially what we have here is a put, which simply uploads a file. It creates a file on the web server. Okay, so what we did essentially was say put /dav_public/foo3.txt. Here's the body of it, and we get a 201 created response. That in and of itself doesn't have the problem in terms of the format string vulnerability. What happens, where the format string vulnerability happens, is in the copy function. So we've uploaded this file. Let me just change that to a 3. We've uploaded this file, and then using the copy function, we essentially give it a destination. Let me try and give that a larger size so you can see it. Okay, here we have destination. Now, we've telnetted in over HTTP, but we've set the scheme to HTTPS. So if we press enter here, we get a bad gateway. Destination URI refers to a different scheme or port, and we can see this HTTPS, essentially. So if we modify this and change the scheme to %ends, we should get an access violation in Apache. There we go. Okay? Sorry, let me just... The instruction, this is in Apache.exe. The instruction at 6FF96342 referenced memory at 0000. The memory couldn't be read, which is interesting because it should have been writing. Okay, essentially this is where the format string vulnerability lies anyway. So in terms of approaches to exploiting this, we have various options available to us. We could overwrite a save return address on the stack. We could overwrite an exception handler, or the unhandled exception filter, which is always found at this location. So we can guarantee, if we overwrite this and cause an access violation, we can get back to our code essentially. The problem with using a save return address is it moves. We will be, in terms of the exploit I'm demonstrating, we will be overwriting the save return address, and I'll come into the reasons why we're not using the unhandled exception filter in a second. The location of the stack changes. It's often found around 320 BD B8, often found around 310 BD B8, 324 BD B8. So we have choices basically, and we have to say which one comes up most often, and use that. Now, the reason we're going to overwrite the save return address here is essentially after Slammer and the code I released at Black Hat last time and it being used as a template, I don't want to give reliable code. Overwriting the save return address is not reliable here. It works maybe 1 times out of 10. Now, anyone who actually sits down and reads this stuff is going to have to make some major modifications to make this guaranteed to work all the time, because I don't want to be writing code that's going to be plugged straight into a worm again. We're going to be using the, remember we had with specifiers, and I talked about using %hx. We can use the same technique for the %n specifier. We're going to do a 3-stage overwrite, as opposed to writing a complete D word, 4 bytes in other words, with a single value. Let me get to that first actually. Because of the location of our exploit, where our exploit code is going to be, is a very big number. It's much bigger than our 0012FF00. We get into all kinds of problems, and it's a nightmare. So what we can do is instead of using a single D-word overwrite, we can do it in stages. So first off, if this is by the way, this is from, here's one I made earlier kind of things. Our save return address that we've chosen can be found most often at 03220 BD-B8. And when it's this color blue, that's what it is beforehand. Using the %hn specifier, we're going to overwrite, first off, the 2 middle bytes. And that means essentially we don't need to format, output a large number of bytes to overwrite just 2 bytes, 65,000 is the max we need to go to. We don't even need to go that far. We're essentially going to write about 200 bytes into that. So ECX will overwrite this part here. The next thing we do, again using the %hn specifier, is overwrite these 2 bytes of the save return address. And then finally, we overwrite, these 4 here with nulls, essentially. So demonstrating this, if this is the save return address in memory, what we do is first off overwrite these 2, then these 2, then these 4. That allows us to completely gain control of the save return address, and when the function returns, it returns to a location of our choosing. And that's using the %hn specifier. Now, I'll show you the code. At the end here, does highlighting it make it more difficult to see? If I scroll up. Okay, I'll read it to you anyway. What we're doing is using a %hn specifier there, then writing another 352 bytes out, writing that to the next 2 bytes along, and then calling %n to overwrite 4 bytes back kind of thing. So because this is on the stack, we can control what addresses we want to write to. So essentially, we're overwriting from 0320BD-B9, so that's the, going back here. B9 starts here, so we overwrite these two. We also put on the stack BA, and that overwrites from there. And then we go back to B5, which overwrites from there. So that's the stages in which we're doing this. Right. So in terms of exploitation, as I said, this is going to be unreliable. Oh, in terms of the actual exploit we're doing, it's very, very simple, nothing fancy. We're just calling winexec, launching cmd/c, doing a directory listing and piping it out to a file orac.txt. Doesn't exist at the moment. Okay, so it worked first time. That's it was supposed to work like after the fifth time, but it's worked first time. Okay, we've reached a breakpoint. Now again, because it's for demonstration purposes, I want to halt the execution. So if we look here, at the end of the code is FFDO is where we're calling EAX, and a couple of nops here, and our breakpoint there. Okay, so if we look for that file, it wasn't found initially. If we do a directory listing, it's now found, kind of thing. So we've managed to execute arbitrary code, spawned cmd.exe, did a directory listing, piped it out to orac.txt. So if I stop that, if I do it again, it should, this is where it's unreliable because I'm overwriting a save return address. We tried to write to 320BD-B9 this time, but that memory's not been initialized. That's why we get this access violation. So going through it, it probably works 1 time out of 10. Again, doesn't work. This is why you would probably go for something like the unfiltered exception handler, because it's guaranteed to be in the right location at the right time, always. Okay, so we can see it's working, 1 time out of every few. Yep. Okay, we can see here actually the ESP is actually 0314, so we're off. Basically, we're off target. If we actually go to that address though, 0314 BDB8. Okay, this here is the save return address, these 4 bytes here. So if we step through this and change, we can see ECX here is 0320 BDB9. If I change that to 14, actually let me just delete this, delete orac.txt. So if we then step through that, we can see, you guys at the back probably won't see it, but this has just changed red here. This 01, BF and 01 has changed to red, so that means data has just changed in there. So we've just gained control of 2 bytes, the middle 2 bytes of the save return address. If we F5, we get another access violation, but if we change it to 14 here, we'll see the next 2 bytes along. These 2 bytes here of the save return address are going to change. Okay, so we've now got written in here BF2003. If we F5 that, we now have the next access violation where if we move up slightly, we can see that the 7E here and these 3 bytes here are going to be overwritten. Sorry, I need to change it to 14. Right, 14. F10. No. Okay, so we've now overwritten the last byte of the save return address with 00. So our new save return address is 0320BF00, which is somewhere in the middle of our exploit code. I'm just going to change this to 14, by the way, and continue execution as if we had guessed the right location. So we F5 that. We get a user breakpoint called from code at 314, blah, blah, an address on the stack. So we've executed through our code. If we then, we've just deleted orec.txt, and it's back again, down orec.txt. So essentially that's what's going on. We're using that three-stage overwrite to overwrite the save return address. So that's essentially how it can be done. And because Oracle, Oracle application service restarts, even if you're using a crappy exploit like the one I've coded here, you're guaranteed, it's going to work one time out of, the number of attempts you try it, kind of thing. So you just keep on retrying because it's restarted every time access violates. Well, it's lucky it worked first time anyway. Okay, so obviously once you've gained control of the application server, you're essentially through the organization's firewall. Now, if they don't have another firewall separating their database servers, then you can, use any port on the actual database server itself to try and gain control. But of course, you can, if there's communication with the back-end database server, we can go through the allowed channel through the firewall anyway, between the web server and the database server, and exploit buffer overflows within the listener or within Oracle itself. Presenting an overly long username to Oracle database server allows us to overwrite a save return address on the stack and allows us to gain control. In terms of exploiting that, actually, unfortunately, the most efficient way of doing that is actually overwriting the exception handler on the stack to gain control, which means once you've done that, you need to try and recover the program's execution, otherwise it will die. And that's a very, very noisy problem. People will notice something's going wrong. So, okay. Are there any questions? No questions? Is the moon made of cheese kind of questions? No? Oh, one. Yeah, go ahead. Yes, there's a patch on the Metalink site. The only problem is if you are evaluating Oracle or Oracle Application Server and you haven't bought it yet, you don't get access to that patch. It's only paying customers that are allowed the patches. So yes, there is a patch, and that's available from the Metalink site. Thanks for bringing that up. I should have actually had that in the presentation. Any other questions? Sure. Well, it's actually, you can code an exploit that basically works 100% of the time, and you clean up after it. And because it's in the actual logging process where the problem lies, you gain control before it logs. So if someone's doing, using a dumb exploit like this one, then yeah, you'll notice something's going wrong, kind of thing. But if it's done properly, then no, you'll probably not notice something's going wrong. Of course, you should turn off WebDAV for a start. That will, save you from this problem because it's really bad to have a production server with WebDAV enabled on it. You don't need a user ID or password to use it either. So it's very, a big threat in terms of having an application server sat there. So first thing is turn off WebDAV, and that, even without a patch, that's going to save you from this exploitation of this problem. No more questions? Okay, well, thank you very much for coming, and I hope you've managed to derive something useful out of this talk.